So welcome back, everybody. As I said yesterday, we want to use these Tuesday lectures as a kind of flipped classroom. I don't know how familiar you are with that concept. It means typically that we will give you some kind of reading assignments, perhaps assignments connected with the weekly exercises and the projects. Then we will have some small additional lectures now and then, but then questions and discussions. So we will typically be three of us. Victor and Amanda will be here as well, not today, because today I just wanted to use today as a way to bring up some of the formalism which we did not fulfill yesterday, and then point to the weekly exercises tomorrow. And I also wanted to repeat many of the messages which I gave yesterday, because some of you have not been able to enlist before today. So that means that you haven't gotten the emails, you haven't been able to log into Canvas, etc., etc. So I hope you don't get offended if I repeat now for 10 minutes, roughly, some of the information which I gave yesterday. Is that okay with you guys? So if you don't want to listen, you can do something else. I don't get offended if you don't do if you do something else, okay? Okay, so just one thing. So this is, as you can see, is not the optimal place for, let's say, a regular lecture. But if you look at the screens here, hopefully you can see most of the information. And can everybody hear well? So there's no problem with the sound, because sometimes this place has actually been a little bit up and down when it comes to the technology. Sometimes the screens just go off, and then we have to reboot everything. So let's just cross fingers and hope for the best. So the official website, and this is where you can start. And when you then click on autumn 26, then you get to the what we can call the official website for this course this semester. And you have the schedule here. So if you look into the schedule, what things which you will see then are, and I take this mode, which is better. You will see now that I have uploaded the video from yesterday. And for those of you who are already registered, you've probably gotten the information through Canvas about the movie from yesterday, the video of yesterday's lecture. But you can always click on those links, which if you look up there on the screens, you will see the video of the lectures, the whiteboard notes, and the teaching material. So that's one source of information, which lies in the what you might call the official domain of the university. Now, in order to avoid confusion, I've obviously duplicated and triplicated all the information in different channels. So I hope I won't confuse you fully, and you can see the wood for the trees. Skogen for bartrær. That's the English way of saying that for the native speaking. So I've added some slides, which will give you also a taste of what we will be doing in these sessions. Then, if you scroll down, you will find the teachers. By some funny reason, this is a site which is not allowed to be translated into English. I don't know why. What you will also find is the link to the teaching material. Now, one thing I wanted to emphasize, for those of you who were not able to register and haven't gotten the emails, as those of you who are registered, because if you're registered, you will get emails as well, but all the information is actually also presented on the official website. Now, I know that many of you come from different places, and you may not know anyone here, or you may know few people. So one of the things which we typically do every semester, because we encourage you guys to work together, you can hand in a common report, common solution to the exercises, is to go to that website and then just write your information and say that I would like to team up with somebody. So if you're okay with that, we will try to make teams of 2 to 3 people. So we make suggestions. It may not work, but we never know. It's a try. So I try to put people together according to interests, scientific interests, and also background. That okay? So take a look at that one if you want to team up. it's always, I mean, we have students, participants in this course come from humanities, social sciences, we have people from economy, we have people from medicine, and we have people essentially from all departments in the College of Natural Science, Matnat-fakultetet. So we are a pretty broad and scattered group, which means that it's also a course which is not always easy to teach because people have different backgrounds. So that's one of the things I wanted to bring up. Then, if you then go back a little bit here and scroll down, you will find the teaching material. So one thing which I would like to emphasize is that you will find the in the folder. So let me just point to that folder. So if you go into the doc, this is the GitHub address. If you click on code here, you can actually download everything and use it as you want. And I actually want you to use it as you want. So this is one of my hobby horses. I think science should be freely available and open to everybody. And I'm pretty proud. Like once I got an email from somebody from Mauritius, and I had to look it up on the map. It's an island north of Madagascar. And that person had been using the material. I think this is the way science should be. And that's why this is fully open. You can use it as you want. If you look at the material, you have the book as a PDF file. And if you click on that link, you will find the lectures book. This is the one which I refer to when I give you reading assignments, and also during the lectures, I will point to specific sections. Like in the linear algebra, there is a lot of linear algebra in chapter 1. That is meant as a background. So I will not teach linear algebra, but I will use linear algebra. And I will state the theorems, and I will use them. But then you can look up the linear algebra chapter and just remind yourself about some of these hidden gems, which you may have forgotten from linear algebra. You will probably also notice that linear algebra is one of my favorite topics. Then you have all the programs for every chapter, and you can use them and look at them if you are a little bit stuck with exercises and projects. So they also described in the main text. If you then go to lecture notes, this is where the Jupyter book resides. And as I mentioned yesterday, you have all the chapters as Jupyter notebooks. And clearly one of the things which is nice with a Jupyter notebook, as you can see here, if I click on any of these, you can download, if you're not familiar with that, you can download this one as a Jupyter notebook. And then you can run it on your local laptop as you want. Okay? Any questions about these practicalities? So I'm sorry for repeating, but I mean, the first week we have lots of people who were not able to register and did not have access to this information here. And it's also a good way. I think it's good to have things repeated, right? I need it normally. I'm pretty slow learner. So if we go back, I wanted to mention something which I have also, one of the things which we are going to use quite a lot is the weekly material. So I will send everybody a weekly email before the week begins, preferentially end of this week, beginning of the weekend, so that you can look at things for Monday and Tuesday. And then the weekly material is obviously incorporated as a Jupyter book, as a PDF, etc. And you can just access it from the week which we are in. Now it's week 34. But I will point to these things for you guys. One more thing. This is something which we added now. So we have a guidance on how to use large language models like Claude, ChatGPT, and so on. These are things which we encourage you to use. But it means it also has some, it brings in some constraints on the projects. But since we are advocating the usage of these, what we have done, if you go to this folder here, which is new, using LLMs, you will find guides on how to use these tools efficiently. So you have Claude, ChatGPT, Gemini, GitHub Copilot. So take a look at those files, and these are things which we will discuss during the lab sessions. So these are tools which are extremely powerful. And as I mentioned yesterday, this is a course which is overpopulated with solutions to any problem you may think of in any course on machine learning. And that means that we can focus a lot on the insights about what goes on behind the curtains. We are coming back to many of these things here, but take a look at these instructions and you can pick the one which is your favorite. There is a catch, however, and this deals with money. So the university does not offer you the professional licenses for Claude, ChatGPT, etc. The university has a ChatGPT UIO, which is more limited. So using some of the softwares like for Claude requires that you have a subscription. So just keep that in mind. Okay? So how many of you do have a subscription to a large language model? Some of you have, yeah. The price tag is in the order of 100 to 200 krona per month, but you can jump off anytime. And there's a big difference between the free version and the paid version. There's really a big difference. So things come, some things are not for free. Everything which I put, so that's why you will find so many Jupyter notebooks fully for free. So if you use the material here, actually you don't need to use these language models. Okay, any questions about practicalities? Okay, so what I want to do now is to say a little bit about where we landed yesterday. And the slides which you will see for today, they contain a little bit of the style which we are going to use in these Tuesday sessions. But as I said, I'm going to lecture more today, but I will try to break with some questions. And then the idea is to try to finalize the discussion on linear regression so that we can start coding tomorrow. And I want to point to the coding examples which we have for tomorrow as well, and give you enough hints that you can get started. Any questions, guys? Okay, so I'm going to skip this one, and I'm going to bring up the, let me find them here. So these are the slides which you also have access to. And I'm going quickly to switch over to my whiteboard so we can slow down the pace. But what these slides contain is a kind of summary of what we did yesterday, where we motivated for linear regression, why we do linear regression at all. A little bit about inputs, outputs. This is just a reminder of where we ended yesterday. And then we are going to just quickly remind you some of these properties. And next week, we are going to look at other types of regression and also look at the statistical interpretation. And there is a stop now and then where we want you to think a little bit. So linear regression, as I said yesterday, this is a method of choice for fitting a continuous function. And if you can fit something with a polynomial approximation or with linear regression in general, and that gives you a perfect fit to the data, then you're basically done. There is no point in using advanced fancy methods. It's cheap, it's quick numerically, but everything which is cheap obviously comes with a price. And one of these prices is that some of the matrices which we deal with cannot be inverted because we have strong correlations in the data sets. The other thing is that we can derive analytical expressions, we can do statistical properties, so we can bring in many of the basic elements which we are going to use again and again in machine learning. There is an analytical relation with probabilistic interpretation, which we will discuss next week. And it's also the natural place where we meet the bias variance trade-off and some other quantities, which we will also discuss in the coming weeks. These are important tools in the analysis of a given model and a given algorithm. which in some cases actually do have analytical solutions. And there's a further reading if you want to look at that. Actually, this paper by Mehta et al. Is an excellent paper. It's actually really good, a good read if you want to take a look at it. So let me quickly remind you of some of the things we did yesterday. We defined inputs and outputs. And you may see that in the literature, sometimes these have different names like input features or predictors. And then we have the outputs, which sometimes are also called the response to something. But I will simply use input and output. Then we have a data set where we may want to fit a probability distribution. So some of you may not have had statistics. So this means actually what is the likelihood of Y? The bar here means given X. And then, or we may just fit a function. This is what we are going to do now. We are going to fit a function. We're not going to fit a probability. That's something which comes later. And then we have a given number of cases. We can have one output per case. We can have also P inputs for case. So, and this leads to a matrix which we call the design matrix, which we set up yesterday. I'm going to remind you of these things. And then before we move on. So here's a simple case of a data set. So what I'm going to do now, from now on, and you will see this again, is that this function f of x or y of x, which I put here, which we assume exists, is going to be approximated with a function y tilde of x. So this will be the example if you fit a fifth order polynomial with 100 points. And if you do that, there is a simple thing here. You have 6 predictors, which are the parameters. I will often call these for parameters. The intercept is where this line crosses the y-axis. This is something we will come back to next week, how to deal with the intercept, because that can often gauge a lot the fitting. And we have one row per data point. And in each row here, we have columns, which are then containing these predictors or features or parameters. In this case, this is a simple program where we set up this design matrix. And this is an example which you will use in the weekly exercises this week. So we set up n 100 points. We define x between 0 and 1. This is the function. And I guess this is something you have done many, many times. So this is something you could use when you're solving the exercises tomorrow. And then we are setting up this matrix, which is going to be an n times 6. And that's the way here as you would set up this matrix. So if you have another data set, there is a popular data set, which we are going to look at later, which is called the Taiwan credit card data. And this is a classification problem. And it has 30,000 entries. And it simply takes whether somebody will pay the credit card debt or not. So this is a yes-no case. It's a classification. It's a binary case. And the features which you have, or these attributes, so what I yesterday called features or properties, also called attributes. So this will be the columns in this matrix X. They contain data about sex, education, employment status, age, etc. of the credit card holder. And then you can make a model and make a prediction whether this person will pay the credit card debt or not. Unfortunately, there's a bias on students. The students tend to be a large group of people who are delayed with the credit card debt. I was one of those. We actually had, I don't know if you know about this, but in the old days, we had something called checks. I guess many of you have never seen that before. And you would just write out the sum, and then the owner of a property would just cash in the check in the bank. If you bended it, the check, then the machine could not read it automatically. And then your account would be charged typically 2 weeks later. So this was a trick which we use as students, because we knew then that the account would be charged later, because the check had to be written manually. So many tricks to delay payments when you are a student, then you have little money. Okay. So question to you guys. Let's just take some few minutes. So I just wanted to give you a kind of a break here. And if you look at this case with a fifth order polynomial, what are the number of entries and the number of p's, the matrix which you're setting up? You can look back at this example. And we're not going to spend so much time, but when we use this class as a flipped classroom, then this will be exercises which we would use more time on. And the questions will not perhaps be as simple as this one. So talk to your neighbor a little bit, and then we just break 1 minute, and then I'm just going to ask what these numbers are. Is that okay? This is also a unique way of getting to know your neighbors. Yeah, let's just take 1 minute and
Klariga finna dessa slag GitHub. Oops. That weekly material. Thank you.
Four slides.
weekly material, week 34. Yeah. Okay.
Vale, todo.
Yeah. Perfect. Hello. Okay. Cool. Okay, guys, should we stop here? So as I said, I mean, today we are not going to use this as a kind of flipped classroom. And I'm sorry to break the discussions which you guys have, but I just wanted to give you the kind of flair of what we will be doing. Yeah.
Degree is 5.
Yeah.
So we have 6 features.
Six features. Yeah. So what you will see in the slides this week is that you also see the answers. But next week, we will not have the answers. So we have to discuss them, right? And we will spend a little bit more time. So what you will see now is something like this, because if you access the slides, you can then see for the degree 5 example, we have n equal 100 and p equals 6. So degree 5 plus the intercept. So your matrix, your data matrix, the one you feed in, is 100 times 6 matrix. Now, there is something which is important to think about these methods. And that has to do with the dimensionality of these matrices. So typically for linear regression, you have much fewer or at most as many features as data points. Because if you have too many features, suppose you're dealing with cancer research and you want to find out which features in your DNA is responsible for that type of cancer, you can have millions of features. And that means that you will have to deal with matrices of dimensionality million times millions. That becomes not very practical. So just keep in mind that even if these methods are simple, they have some limitations. And you can see here that if you now change with n equal 8, which is smaller than the number of features, then you have more unknowns than equations. And that means that you have infinitely many polynomials which pass through all 8 points. That means for us that there are infinitely many solutions to the problem. Then linear regression becomes just useless because you cannot point to a specific model which is the best one. So just keep these small things in mind. That's why I bring up these kind of things. And when we are using these Tuesday sessions, we will have much more discussions. So today was more meant to give you a kind of feeling of how we will use these sessions. So typically, yeah. You cannot use it when the number of features is larger than the number of data points. So just keep that in mind. And this is the kind of problem which we have set up. And our model is a linear one in the unknown parameters theta. Now, there is an epsilon here. And I wanted to say something about this epsilon, because this is an important assumption about the data, which we will use next week when we come to a statistical description. So in linear regression, and in many of the things which you will see, we are making an assumption about the data that one, there is a function which we can approximate. We don't know this function, but we can approximate it with some model. So our model is given by this matrix times the unknown parameters. Then we are adding one thing. We are adding a noise. So we assume that the data set which we have has some deterministic model or a function which we don't know. This f of x, which is unknown to us, which we want to approximate. This can be approximated with a neural network, with a linear regression model, whatever. But then there is a noise which we assume is distributed by a normal distribution. That means a mean value equal to 0, a Gaussian with mean value 0, and variance equal to 1. So this epsilon is a normal distributed variable which brings in noise in the data. But in the fitting now, we are going to leave that out, but we will bring it back when we discuss the connection with statistics. Okay, so just as a small comment about the data which we are going to look at. Then I wanted to repeat some of the things which we discussed yesterday. So it's a little bit repetition. So when we looked at this parameterization, there is nothing which forces the columns to be powers of x. That is the simplest thing we can do, a polynomial. But these could be functions like cosine, sines, or whatever is appropriate for your scientific problem. So this would typically be what we call a basis expansion. So let me just now ask another question here. And when we say linear, we actually mean linear in the parameter theta. So take a look at this one, and then we just break another 1-2 minutes. And if you look at these questions, you can just think, what is a linear model here? And what is not a linear model? If you look at these, all these are ways to model a data set, right? So just give it a thought. And if you are a little impatient like me, you can scroll down the slide and you will find the answer. But just give it a thought and just talk to your neighbor a little bit and see which one of these are linear ones in the unknown parameter theta and which are non-linear. Okay, guys, should we stop here? Again, I'm a little bit sorry for interrupting the nice discussions you're having, but I put up the answer here. I don't know if that agrees with what you guys came up with, but you see the kind of setting which I would like to have during the Tuesday sessions. So a little bit lectures, repetition of things, and then to point out things which are relevant for the things we are going to solve and study. So during these Tuesday sessions, we will spend more time on these kind of discussions. But I hope that you see the kind of setting, and I hope you will like it, obviously. To me, it's a much more fun way to teach. Okay, so what I'm going to do now, after some quick things, is actually, this is also where we ended yesterday. And now I'm going to set up the optimization by itself. So the optimization part is the one which is the delicate one. And the project one is going to deal with different ways to do the optimization. So what I'm going to do now after this slide here is to switch back to the whiteboard, if that's okay. Okay? So then it will be just more like a regular lecture. Any questions? So feel free to use these slides as you want. There's much more, and questions like these with answers. And it's a way to, one of the reasons why I bring it up is that it's also a way to refresh linear algebra. And most of you had linear algebra in your first year at university. And if you're like me, this is was just gone, right? So typically when you came to the new semester and the teachers would ask you, yeah, you have seen this before. No, I never seen this before. So take a look at these linear algebra things, because machine learning is to a very large extent linear algebra and statistics and optimization. So such an exciting thing like matrix vector and matrix vector multiplications is something which is done repeatedly at the heart of all these algorithms. So when you come to neural network, you will be so excited about linear algebra that you don't know where to go, okay? I'm joking. But it's at the heart of all we do, there's linear algebra and statistics. So let's change to the whiteboard and bring up some new stuff. Let's see if it wants to bring it up. I have to allow it to connect. There we are. Okay. So the thing which we are going to do now with this cost function, so I'm going to write this in a simpler way. So I'm going to write it just as a function of theta. And we are going to look at the mean squared error, which is a popular way to assess whether the model we have made is okay or not. And it's written like a sample expectation value. So it runs over all the data points which we have. So if we have 100 observations, these are the 100 observations which we're using. And then we have the data points minus the model which we have made. So keep in mind now that we are making an assumption that y of I is given by a function which we have no idea what it looks like. So we are assuming that for linear regression, that there is a continuous function which describes the data, but we don't know this function. And then we have some normally distributed noise. So what you will typically see, just to remind you of some statistics, is that this follows a normal distribution. So the latter one was my attempt of making the letter n. So this is the mean value, mu, which is 0. And this is the variance, which we typically set to 1. But normally we don't know what the variance is. But now we're just setting it to 1, and then we have a normal distribution. So this is an assumption about the data. So what we are doing is to make a model, as we said yesterday. And this model is y of I tilde. And this is going to approximate the function x of I. And in our case, for the polynomial, which is the example we looked at, then this y of I is simply given by a function of j here, sum over j, up to the polynomial degree we are interested in. And then we have some x of I to the power of j multiplied with these parameters theta of j. So this is basically the model which we have been looking at. but we can make it more general. We don't need to have a polynomial. So if we want to make this design matrix a little bit more general, we would then simply set in the different elements in the columns and just label them with the matrix elements. So let us do that. So this was a polynomial case, which is the case we have in many of the examples. But let me now just define this design matrix. And this matrix is given by x00, x01, and then x0 to p minus 1. That's the last column. And we call these columns for features or properties or attributes, etc. They describe something. In the credit card data, one column could be the age of the credit card holder. Another column could be the employment degree, etc., etc. And then we have x10, etc., up to x1, p minus 1, and then down to xn. So we have n data points, and all the way up to xn minus 1 of p minus 1. And then each column represents some specific properties of the data. If this is a polynomial, in the case of a polynomial, this first column is just ones. The next column is x to the power of 1. And the final column is x to the power of p minus 1. And then you have the different x values. Now, when we then look at the cost function, the c of theta, this kind of definition, what we would have then is a sum. If we now write out the sums here of I 0 up to n minus 1, we would have y of I minus, and then we have a sum over j. So we are multiplying the matrix with, so we have xi of j multiplied with theta j squared. So this is the model which we have plugged in. So this one is nothing but y of I tilde. Then, since we want to optimize, we want to find the optimal parameters. What we need then is to calculate dc of d theta as a function of d theta j. And each one of these are quantities we want to drive to 0. Let me take this one away. Okay. So that means that when we take the derivatives, this is simply going to be, if we look at one of these, this is going to be equal to minus 2 divided by n. I'm going to have a sum here of I equals 0 up to n minus 1. I'm going to have an xij, and this is multiplied with y of I minus, and then I have my sum here, where I'm now taking out the parameter, one of the parameters. So this is simply going to look like a sum over k, of this theta of k, of xik, like this. And we want this one to be 0. Now, next week, we are going to exercise a little bit with matrices and vectors and their derivatives. But if you look at this one and you write it out, and the simplest case you can take, just do that as a small exercise. Just take that as a small exercise and just set p equal to 2 and n equal to 2. And then see what this looks like. Because if you now look at that equation and you want to write it out as a vector, because keep in mind now that this is just one row of all the j values which we have here. So we have an equation for theta 0, for theta 1, all the values theta, the unknown quantities. So we can rewrite that as a gradient. And this is something I just want you to take a look at. So instead of looking at just one row at a time, we look at the gradient. So this becomes a vector of C. And I'm going to skip, now I keep theta here, but I will skip theta just for simplicity. So we don't have too much notational clutter in the equations. Now, if you look at that one, which we want to drive to 0, this is something when you inspect this equation here, you can write this out as minus 2 divided by n. And then we have the transpose of that matrix, the vector y, this is a vector, minus the matrix x times the vector theta. So I'm not very good at making bold-face symbols when I write by hand. In the lecture notes, vectors will be bold-faced. But in the lectures here, I will use arrows to indicate that these are vectors. So the gradient is a vector, right? Because every row which we are setting up is given by this quantity. And we can compactify that as a vector, which is the gradient here. And this is the equation. So let me just finish this one, and then we take a small break. So we want this to be 0. So that means that we can multiply away minus 2 divided by n. In some textbooks, you will see that they have skipped the factor of n, or they may have written 2 divided by n, because when you then take the derivative, you get rid of the number 2. But since we have this equality with 0 here, we can just multiply away this one. And that means that what we get is simply now that x transpose times x is not multiplied with a vector theta. And now I'm going to put in a hat. I'm going to say what this hat is. X of t or multiplied with a vector y. So this is also a vector. So that means that the unknown parameter, theta, this is a vector, is given by x transpose times x, the inverse, times x transpose times y. So everything on the right-hand side is known. This is something which we will put a subscript OLS, ordinary least squares. The hat is a common notation in statistics, which means the optimal parameter, which now optimizes the mean squared error. So this is the parameter which gives you a mean squared error, which ideally then should be 0. Ideally. But it's never going to be 0, but it's going to be small. So this is the one with the data set which optimizes the parameters here. Then that means that y tilde, and now I'm skipping the vector sign, optimal, is now given by x times this theta, and I'm skipping the vector sign here because else there is too much clutter. So this is the optimal parameter. So when I put opt here, it means the optimal parameter. And I put this subscript to ordinary least squares because this is going to be the kind of notation we will be using just to identify what kind of method it came from. Now you can also, I'm going to add one thing, and you will practice this next week in the exercises. You can take the second derivative. And the second derivative has to be a matrix. And this is a very important quantity. So I can now calculate the second derivative of this cost function. And you will find that when I take the derivative with respect to theta, this is simply, so you have minus x times theta, theta disappears. You have x transpose and 2 of n. And this is 2 divided by n, x transpose times x. This matrix is one of the bottlenecks in the optimizations. If you have a huge problem in like a neural network with millions of parameters, that matrix will have a dimensionality of 1 million times 1 million. In the optimization, you're using Newton's method, which is a Taylor expansion, which stops at the second derivative. This is a second derivative. And this is an ugly quantity because it can be huge and you don't want to calculate it. This has a name in the optimization literature and in statistics as well. It's called the Hessian matrix. For linear regression, this matrix is positive definite. Sorry, semi-positive definite. It means that all eigenvalues are larger or equal than 0. That means that this is an exact convex problem with a global minimum. We will come back to that after the break, where we're going to prove it, because this is fundamental. Because when you move to neural networks, you may not have a convex problem. Does everybody remember what a convex problem is? Okay, let me bring that up after the break. I tend to go on because when I get excited, I forget about time. And this is one of the topics I like. So let's take a small break, yeah? And then we bring that up after the break, because this is actually very important when we do machine learning. And one of the reasons why linear regressions is such a useful method. So we take a small break. So before the break, what we said is that this optimization problem is actually an optimization problem of a convex function, because the second derivative is larger or equal than 0. So just to quickly remind you of a convexivity and concave problem. So the type of problem which we want to have is a problem of this type here. Suppose we have some parameters here, and we have some value x. So this will be a typical convex problem. And in this case, if we now have a function where this alpha is a function of x in some way, what we have then is that the second derivative of f with respect to x is a function, is something which is larger or equal than 0. Now, that means that there is, in this case, there is a global minimum. A concave problem is the opposite. That's a maximization problem. So this belongs to a minimization. So we are minimizing by obvious reason. We are looking after the minima. Now, what we have in this specific case is that the second derivative of the mean squared error, which I write like this. So this is a matrix, which we call the Hessian matrix. So we are coming back to this. We are going to come back to this many, many times. So this is a Hessian matrix. And it has eigenvalues with, and I'm going to show you that now, with eigenvalues lambda I, which all are larger or equal than 0. So this is called a semi-positive definite matrix. And you probably encountered that in some of the courses in linear algebra. So when all the eigenvalues are positive for the optimization problem, that means that we do actually have a global minimum. And this is one of the reasons, one of the main reasons actually why linear regression is such a popular pedagogical tool, because we know that we have a global minimum. When you come to a neural network, on the other hand, life is going to look much worse. You're going to have a multidimensional surface. And since I am, according to my wife, and my daughter agrees with that, a very one-dimensional character, I can only make a two-dimensional drawing at most. When I move into 3 dimensions, then I'm just lost. But if you think of a 2-dimensional case, no, actually it's a 1-dimensional function. A neural network may actually give you a landscape for optimization which looks like this. So when you use these optimization algorithms, so let's bring back this alpha here, the function as a function of x. Ideally, we want to be here. This is the global minimum, right? But we could be unlucky and we could end here. So that would be a local minimum. So in the optimization algorithms which we are going to use, you can actually be unlucky. And you may not even have a function which is convex. So this is the problem when you go into multidimensional problems like you have with neural networks. So this is something which we would call a local minima. Local minimum. Another case which is really bad and which can be difficult to observe properly when you do the numerics is a case like this one. So this is actually supposed to be flat. Does anyone remember what you typically call a point like that? Think of horses. What do you put on a horse when you want to ride it, yeah? That's a saddle point, right? So this is a tricky problem because if you look at these cases, these are cases where the derivative of this function is going to be 0 here. It's going to be 0 here, but it's also going to be 0 here. So if your optimization algorithm stops because the gradient is 0, then you may be stuck in unwanted positions. So this is one of the nice things, and also the reason why project number 1 is going to deal with linear regression and the optimization problem, because you know that the quantity you're going to optimize has a global mean. So checking codes against something which can be tested is extremely useful. And you will see that many of the things we will do when we add elements to our projects, we are going to add elements so that we can always check that what we are doing is done correctly. So having things like small tests, so-called unit tests, is something which is essential when we develop a larger project. So this is, again, one of the motivations why we start with linear regression. Although many people may say, hey, this equation which you have here, this doesn't look like machine learning. But what you could say, as I said yesterday, this is low-level machine learning in the sense that we have an equation which allows us to learn the parameters. So we are learning the optimal parameters. Okay, so now the thing I wanted to show now is that, and this allows me to bring in another topic from linear algebra, which is going to be important for us. So I wanted to say something about, I wanted to prove that this is a convex function, and that the second derivative has eigenvalues which are larger or equal than 0. So how do we show that? Now, there is an important algorithm. And so if you go back to the lecture notes in sections 118 to 120, there is a set of pages which deal with my favorite algorithm in linear algebra. Has any one of you met this algorithm? It has this acronym SVD. Does that ring a bell from linear algebra? So who has never heard of it? Okay. It's called singular value decomposition, SVD. So we are going to use that to prove that this function has eigenvalues which are larger or equal than 0. Okay, so let's do that. I think this is important because when I say that things are like that, sometimes we have to accept it and say that, okay, this is in the books. But now I just wanted to show that. And it allows me to bring back the singular value decomposition, which you will find in these sections here. So that's a reminder about linear algebra. So what does the SVD say? So the SVD says the following. Suppose you have a matrix A. This is any matrix. Now I'm assuming that the matrix has real components, but you can set it up for complex, integers, etc. But I'm assuming now that this is a matrix of dimensionality n times p. Now, one of the reasons why I'm bringing this up is important for us when we do machine learning. So before we move on, let me just bring back this equation here. And this equation hinges on this being a matrix where we cannot write out columns as functions of each other by a constant. So the matrix cannot be singular. So it has to be invertible. Now, if it's not invertible, we cannot use ordinary least squares. Okay? So the singular value is a way to circumvent that, but although it will still keep information about the singularity, but the singular value theorem, singular value decomposition, says that we can decompose any matrix. And we can decompose any matrix in terms of an orthogonal matrix U times the matrix which holds the singular values multiplied with another orthogonal matrix. So this matrix has dimensionality n times n, and I'm going to show you examples of it. This has dimensionality n times p, and this has dimensionality p times p. Now U is an orthogonal matrix, which means that if we perform these matrix operations, it gives us a unitary matrix. No, sorry, a identity matrix. That could be unitary, but I'm sticking with real numbers. So I'm assuming that these are orthogonal matrices. Sorry, VT times V, like that. So that's an important thing. Now, the matrix which has the singular values looks as follows. So the sigma has then singular values, sigma 1 down to sigma p minus 1, and then it has zeros and zeros. And these singular values can be organized. So you can organize them so that sigma 0, actually sigma, they are not degenerate. Sigma 1, sigma 2, this is one way to organize them. And sigma p minus 1 larger than 0. These are called singular values. So as an example, just consider this matrix here. So if you look at sigma, you can take an example like this one, 2, 0, 0, 1, 0, 0. So that's an example of a matrix which contains singular values. So you would have sigma 0 equal to 2 and sigma 1 equal to 1. And the other ones are 0. There's also an important thing to pay attention to. If I perform this matrix multiplication, this gives me elements which are constant along the diagonals. If I take the other one, then this is given by 4, 0, 0, 0, 1, 0, 0, 0, 0. So this has some zeros. So these are things just to keep in mind, because we are going to use that when we are going to look at the proof here, some of these properties. So this is just a quick reminder of the singular value decomposition theorem, which simply states that any matrix can be decomposed like this. Any matrix. So the other thing I wanted to say, since the matrices U and V are orthogonal matrices, it means that every vector, every column of that matrix forms an orthogonal vector. So if you now write out these matrices like U, that would be a matrix which now has a column here. This is a vector, a U1. So this is another way to write a matrix. So this has n minus 1, n orthogonal vectors. And if I take the U of I with the transpose of U of j, this is given by delta ij. And the same if I take V, that is also composed with of these orthogonal vectors. So these are orthogonal matrices. So each column now is given by these vectors, either V or U. And this has the final vector P minus 1. Now, what does this give us when we now look at the matrix which we want to prove has positive or larger than 0 eigenvalues? So keep in mind now that we have said that the singular value decomposition gives us values here which are larger than 0. Okay, that's important. So when we now look at the matrix, which we both have to invert, and we can use for the second derivative. So the second derivative, the Hessian, is actually given by this matrix product. We now decompose it with a singular value decomposition. So this contains sigma t times U transpose times U times sigma times V of t. And we know that this one is given by the identity matrix, because these are orthogonal matrices. So this object which you see here is an n times n matrix. This is an n times p, and this is an p times n. And this final matrix has to have dimensionality p times p. This is also important for us, this p times p, because if you have 1,000 data points, n, but only 5 features, you only need to invert a 5 by 5 matrix. So that is also one of the reasons why these methods work best when you have less features than data points. And typically what you want to have is something like you can have many data points, but you would typically not have more than 100 to 1,000 features. Then there are methods to actually take away those which are less important. We will come back to that. Now, if you look at this now, what you have is V times this sigma transpose times sigma times V of t. And you do the math. This is a P times P matrix at the end. If you look at this one, take a closer look at that one with the example we had previously. If you look at what we did here, you see that this is now just a 2 by 2 matrix in this specific case, and it has only non-zero elements, only non-zero, or it contains only the singular values. Now, there's another thing which I'm going to say here, is that you can show that since these are orthogonal matrices, this matrix is a diagonal matrix only. The matrix sigma transpose times sigma is a diagonal matrix. What you have then is that the matrix V times sigma t times sigma is actually equal, because this is just a diagonal matrix, you can actually write it like this. Okay, so what I'm going to do then is now to set up things a little bit differently. So when we do that, we have X transpose times X. And let's now just do this. And what we get then is a sigma transpose times sigma. So I could use the unitarity now if I wanted to, but I'm not going to do that because I'm going to multiply this with V. Now, when I take V transpose times V, I just replace that one with the identity. And then I have X transpose times X times V. And that is equal to this matrix, which has only elements along the diagonal, multiplied with V. Now I pick one of the vectors here, only one of the vectors. So I'm just going to pick, let's say, vector V of I. And this is going to be equal to sigma of I squared multiplied with V of I. So what kind of equation is that, if you look at it? It has a name in the numerical or linear algebra. Anyone who remembers what we typically call this type of problems? It begins with an E. Yeah. This is an eigenvalue problem. This is simply an eigenvalue problem. Because if I pick I only picked one of the vectors now. These are orthogonal vectors. So when you diagonalize a problem, you obviously have orthogonal eigenvectors. So this is an eigenvalue problem. And all these sigmas and sigma i's are all larger than 0 or equal to 0. So this is a proof that this is a semi-positive definite matrix, because all the eigenvalues are large equal to 0. And that leads to a convex problem with a global minimum. So the eigenvalues of that matrix are all positive or larger than 0 or equal to 0. So this is a semi-positive definite matrix. And this is the way you can prove that this matrix actually leads to a convex problem with a global minimum. Okay, this was a digression. And it allowed me to introduce the singular value decomposition because I'm going to bring that up again and again next week in particular. Now, since we now mentioned this with the problem of the dimensionality, no, of the case where we could have a singular matrix. So if we look at the ordinary least square equations, and this is equal to the optimal parameters for OLS. If this object is singular, then we cannot solve the equation. Then no OLS solution. I guess that's pretty obvious, right? So that means that if the columns of that matrix are dependent on each other, then or there's a real dependence, which is often the case in data sets. If you have a polynomial, then you will often avoid that problem. But in general, this is a little bit problematic, and this is also why we use the singular value decomposition to perform the calculation of the inverse of that matrix. And that's called the pseudo-inverse. We will come back to that next week. Now, there is a cheap trick which people used before to avoid singularities. So if you go into many numerical codes, especially if you look into old Fortran codes, you will sometimes see 0 defined to 10 to the minus 8 or something like that. So it's not 0, but it's a small number. So what kind of trick can you use to avoid a singularity when you invert that matrix? Problems with singularities. Is there a simple trick you can do with the matrix? This is a cheat. And people use that in case you had the unstable numerical results. Has anyone of you seen that? It's a cheap trick by which you can avoid that matrix gives you a singularity problem. You may not have seen, nobody has taught you to cheat, right? Okay, so this way you can do that is to add a positive number, a small positive number, to the diagonal matrix elements. And then you can show that the matrix then can be inverted. So what many people did in old algorithms, because you didn't have that precision you could achieve numerically, you would often just add a small number to avoid loss of numerical precision and problems with matrix inversions, etc. So if I choose a parameter which I call for lambda, which is larger than 0. If it's 0, then I'm back to the same matrix. And if I then define X transpose a new matrix plus lambda times the identity matrix, then I can invert. Then we can invert X transpose times X plus lambda times identity matrix. So that's a kind of cheap trick. So if you make lambda a small number, you're still hoping that the problem is pretty close to the one you started with. And you will see that this is a kind of trick which was used numerically back in the 50s, 60s, and even 70s. So what that means is that you get a new theta optimal, which now is called ridge, which we will discuss next week. And this is given by the following problem. Plus lambda times the identity matrix, which has dimension P times P. Sorry, P times P. This has also dimension P times P, inverse, and multiplied with X times transpose times y. So this problem is well defined numerically, and it leads to a problem which doesn't have a singularity. Now, this sounds strange, right? Because in a way we are cheating. But what we are going to show is that you can define another optimization problem. So what we can define, and the nice thing here, so something which came originally as a numerical cheat is something which you can justify by optimizing another problem. So the problem to optimize, and we are going to spend some time on this next week and the week thereafter, and you will see that in the exercises as well, is to define a new cost function. Let me just skip the theta dependence. So which we are going to call ridge. And this is given by the standard one which we have before, the mean square error. And then we have our y of I minus, and then we have this sum over j, and then we have the xij times the theta j's squared. So this is nothing but what we have seen till now. But then we have a new term where we put this parameter lambda, and we have a sum over j equals 0 to p minus 1. And then we have this theta j's squared. If I now take the derivative with respect to theta, I will actually get this expression here. So what I'm doing now is to anticipate a result which is going to come and which we will discuss a little bit more next week. But this equation is also something we can write in a compact way. So it's given like this, I equals 0, and minus 1. And now I just rewrite it like y of I minus y of I tilde, which depends on theta squared, plus lambda. And this is normally written as a function like this, the norm 2 squared. So this is called a norm 2 or L2 regularization. You can take the norm 1, which is just the sum of absolute values, and we are going to get another scheme to optimize, which is called lasso optimization. So these are three methods, ordinary least squares, lasso optimization, and ridge optimization, which we are going to play around with. Now, you could say that, hey, with this cheat, I mean, this was just a simple cheat, but you can formalize it and say that now we are optimizing another function. So when I calculate the derivatives here of this function, if I take the derivatives and want to have the gradient of a C ridge, what we will get then is a function. So it's going to look like this. We will have the same derivative which we had when we took the mean square error of y minus x of theta. But then we have plus 2 times lambda multiplied with a sum over all the theta values, and we want that one to be 0. So when we do that, what we get, if we now just rewrite the theta j's in terms of a vector, we get, and what we do now is to multiply with 2 over n. We get rid of the 2's, but if we look at the n's here, so this is pretty common, you take the n, you get n times lambda, but you can always relabel lambda. So it means that lambda, which you're seeing in this next equation, is going to be modified. So when you take these derivatives, so this will be a lambda tilde, but I will just call it, so we just rewrite it in terms of a new lambda and theta, and this is equal to x transpose times y. And that means that theta, the optimal one, ridge, is then equal to this matrix to invert, plus lambda times the identity matrix, inverse, times x times y. So these terms are called regularization terms, and I will come back to that next week, why we call them regularization terms. And it's norm 2 quantity, which we add, which gives us much more flexibility in the optimization. And it avoids zeros. We have also another function, which is called lasso, C lasso, which we will also discuss next week. And that contains the mean squared error. And I'm going to write it in terms of the norm 2, which we introduced yesterday. This is just a mean squared error. But instead of a norm 2, we have a norm 1 of the unknown parameters. And the norm 1 of a vector is actually given by the sum of j and of the absolute values of the elements of the vector. Now, ridge and ordinary least squares are extremely simple to implement. They have actually analytical solutions. Lasso, on the other hand, due to the absolute value, is going to give us problems. And then we have to solve it numerically. So we have to solve everything numerically by inverting matrices, but now we would have to have a gradient method which allows us to solve the lasso equations. Because we don't have these nice analytical solutions, which you see here. So this is a nice analytical solution for the unknown parameters. And then we have, similarly for ordinary least squares, we have this equation here. So everything which you see here, I am bringing this in a very ad hoc way now. But what you will see next week is that we can derive the same equations using a statistical interpretation. And that gives a very elegant way of understanding these additional parameters which we have introduced. So there is some coherence in this kind of ad hoc approach here. But in the beginning, you should keep in mind that in the beginning, this was formulated as a numerical cheat. And then people formulated as an optimization problem with additional constants. Yeah?
Wouldn't it be possible to interpret it as penalizing like ridiculous weights?
Exactly. And you will see that these are normally called these lambdas, often called penalizations. And some people call it regularization, but penalization is actually a better word. That's a very good point. We're going to see that next